Okay, let's go to the course. Okay, everybody. Okay. If you remember, we were talking about arithmetic, and we have already covered addition and subtraction. How could I make it disappear? Last time we did something with that. It should disappear. Maybe I put it here. Okay. So about multimedia, okay, let's go here. Now we are going to talk about multiplication. So as you know, multiplication is a bit more complex than addition and subtraction. How do we do multiplication in a school? How did we learn to do multiplication? So whatever we did in school, we will use it here also. So here in multiplication, let's do something in decimal. I am writing 327 multiplication by 715. What did we do in the multiplication? What we are going to use digits of the second number and multiply them, each of them separately to the first number. Then, after, let's start with this number. You know these things. I just go through it so we could get the same thing in the binary number. So 5 times 7, 35, we have 3. 5 times 2 is 10 plus 3 is 13. And 5 times 3 is 15 plus 1 is 16. Then, when we go for the next digit, then since the value of this is in the 10 position, so we have to shift the result 1 to the left. So 1 times 7, 1 times 2, 1 times 3. For the next digit, which is 7 here, we have to again shift it to left. 7 times 7 is 49, so we have 4 here. 7 times 2 is 14 plus 4 is 18. 7 times 3 is 21 plus 1 is 22. So the result would be 5, 3, 10, 1 plus 6, 7 plus 2, 9 plus 9, 18. 1 plus 1, 2, 5, 13, 3, 2. So the result would be 233,805. So how did we do that? We just multiplied each digit separately, but in the correct position. The same thing we are going to do in binary. I don't know why it's not hiding. There was an option last time that it was hiding. Do you know, could you help me? I don't know. Maybe there should be something like pin. No?
Video panel towards the bottom.
Where is that?
It's towards the bottom.
Fourth of the height floating, this one. Height floating meter. This is, yeah? Yeah. So it was Control Alt press escape to show. Okay. Okay. So that's good. For the time being, it's good. Online people, do you see that? Okay. So Kevin and Max. Okay, Kevin is here. Where is Maximilian? Maximilian, where are you? And here, who do we have? Oh, it's very down. Who is this? I don't see the name. Okay, Tony. Tony, you are very down. Okay, good. Yes, very good. So multiplication, let's go. Start, the first algorithm that we use is just the same thing that I did in the decimal. We call it line multiplication approach. So you see here, this is the multiplier, this is the multiplicand. So we start from the digits of the multiplier. The first digit is 1. So 1 times, since it is binary, it is very simple. It is either 1 or 0. If it is 1, means that the multiplicand just be put there. If it is 0, then it is the multiplication is 0. So it's very simple. So let me do it here, and then we go through that the same thing. So this is 1. 1 times 1000 becomes 1. Then the next digit is 0, but we have to put 0 with one shift to the left. The next digit is 0. Again, we have 0, but with one left shift. And the next digit is 1, so we have 1, 0, 0, 0. Now we are adding these things together. So 0, 0, 0, 1, 0, 0, 1. So the result would be 7-bit number, 7-bit number. We had multiplied 2 4-bit numbers. This result is 7-bit number, which is 100100. The maximum bits for the multiply would be how many? 4-bit by 4-bit. It could go up to 8 bits for the multiplication, okay? So we have to consider 8-bit register for product. The length of the product is the sum of the operand length. Now look at the hardware. The same thing that we did in our procedure, we are doing the same thing in the hardware. So you see here, we have multiplicand, and this let's say both of the multiplicand and multiplier, they are 32 bits. So if they are 32 bits, we put multiplicand as 64 bits. We are filling zeros to the left of the multiplicand. And then we have a 64-bit ALU to add up these values. You see here, we have these values which should be added together. So we have an ALU to add these values, and the product each time should come again to be added and accumulated. So we start adding this, then this, then this, and then the last item. You see here, the multiplicand is, we start with the multiplicand. We look at multiplier. We shift it right. When we shift the multiplier right, we look at the bit which is coming out. The bit is 1. When the bit is 1, then it means that we have to add the multiplicand. We have to put it there. So when this is 1, the multiplicand comes and it will be added to whatever we had before. At the beginning, the product is 0, so 0 will be added to multiplicand, which is 1000. So this is this stage, as you see here, this stage. Then the multiplier shifts right again. The next shift will bring 0 to the right. So if it is 0, then control says, okay, nothing will be added. I forgot to tell you, after each stage, we shift left the multiplicand 1 bit. It is the same thing that we have done here. So this is shift left 1, shift left 2, shift left 3. So we do shift left, and since it is 0, so nothing will be added, and the product is still 1000. The next step, so we go to the next step. The next step, again, we shift the multiplicand by left, one bit left. So the multiplicand is now 1, 0, 0, 0, 2, 2 left, so 0, 0. So this is the multiplicand now. And we look at the bit from multiplier. The next bit from multiplier is still 0. So we don't add anything. It's still the multiplier, the multiplication, it comes out and the product is still there. The next thing would be one shift to the left, the multiplicand. So the multiplicand now becomes this, 1, 0, 0, 0, 0, 0. We shift right the multiplier. The next shift right is this 1. So we have 1 now. Now we have to add this to the product that we have. This is the new multiplicand plus the product that we had. The product that we had was this before. So we are adding them together. The result would become 1, 0, 0, 1, 0, 0, 0. So that would be the result. The same thing that we did in the paper, in the pen and paper work. But as you see here, there are two shifts. One is shifting left of the multiplicand, and then shifting right the multiplier. Shifting right to see what bit is there. Is it 0 or 1? If it is 0, then nothing is added. If it is 1, then multiplicand will be added to the product that we have, the current product that we have here. Okay, clear? The procedure is some kind of taking time to the number of bits that we have. And for each bit, we are doing some steps. Shifting left, the multiplicand, shifting right, the multiplier, and adding if it is 1. So there are 3 things that we are doing in each step, and then the next bit, the next bit, the next bit. So this is how it is done in another example. Let's say that we are going to multiply 2. 2, where is 2? This is 2. 2, 2, 3. 2 by 3. The multiplier is 3. So we do. Let me show you first the algorithm. So again, here you see we start. Where is the thing that I could start? Here, okay. No, not this one. Yes, we start with multiplier. Each stage we shift right multiplier by 1. We shift left multiplicand by 1. So the first initial values, multiplier is 1, 1, which is 3, and multiplicand is 1, 0, which is 2, and the product is 0. The first thing that is that we look, we just add multiplicand to the product because the first digit, the first bit is 1. Since it is 1, we add these things together. If it is 0, we don't add anything. So multiplicand plus product becomes this. Up to now, it is 2. Then we shift left multiplicand. So the multiplicand becomes 1, 0, 0, which is actually 4 in decimal. And we shift right multiplier. Now the bit in the multiplier again is 1. Since it is 1, we add multiplicand to the product, and we put the result here. So now the result is 110. 110. Okay. And again we shift left multiplicand by 1, so the multiplicand becomes 1000, which is 8 in decimal, and we shift right multiplier, so now the bit is 0. Since it is 0, we don't change anything for the product. we again shift left multiplicand, it becomes 1, 0, 0, 0, 0. And again, we shift right multiplier, so it is 0. Since it is 0, we don't add anything to the product. The product is still the same. We shift left multiplier, we shift right the multiplier, is still 0, and that's it. We are done with the bits of multiplier, 4 bits of multiplier. The result would be this, which is 6. 2 times 3 is 6. So we have done it. So this is the hardware that we talked. Initially 0, every time 1 shift left and 1 shift right here for the multiplier. And this is the algorithm. It has 3 steps. In the first step, we test if it is 0 or 1 at the first bit of multiplier. If it is 1, then we have to add multiplicand to product. If it is 0, we don't add. We come here, we shift the multiplicand left, and we shift right the multiplier, and going back again to test the multiplier, the first bit of multiplier, if it is 0 or 1. As you could see, we are doing shifts, 2 shifts. One for multiplier, the other for multiplicand. We may put them together to make it faster. How do we do that? We put multiplier at the left half of the product first, and then we shift them one by one. Yes, we shift them one by one. And since when we are shifting that, we are shifting the multiplicand and the multiplier together, and then with the control, we look at the bit if it is 1 or 0. So that's something that it is faster than what we have talked about before. 1 cycle per partial product. That was 3 steps that we are doing here. We do it 2 steps. 1 shift and 1 addition. If you look at the multiplier, what we have done, we were looking at the multiplier bits, and if it is 0, we didn't add anything. If it is 1, we add a shifted version of the multiplicand to the product. Is that right? So that's what we have done. Adding shifted version of multiplicand to the product. Either it is 1, which will be added. If it is 0, then we don't add anything. If this is the case, could I do it in parallel? Because, for example, if it is 32-bit by 32-bit, I am adding 32 times of these values. Each time shifting left, add, shifting left, add, shifting left, add. So why not doing it in parallel? It is add. So I can do something like that. I know that the first 2 numbers would be multiplicand plus product with sum. And multiplicand plus shifted left 1 bit of multiplicand if it is 1. So I am adding these together at the beginning. If it is 1, then I use this. If it is not 1, I don't use this. And the same thing for shifted left 2 times and shifted left 3 times. So let me write it for you. Let me say that this is multiplicand. So this is multiplicand. And for the simplicity, I assume that the multiplier is 1, 1, 1, 1. If this is the case, what would be the result at the end? The result would be something like that. 1, 0, 1, 0 plus 1, 0, 1, 0 at one position, shift of left. And then 1, 0, 1, 0 shifted 2 times plus 1, 0, 1, 0 shifted 3 times. So these are added together, and the sum, these two sums should be added together. Isn't it true? I add multiplicand with shifted left, then I add shifted left 2 times with multiplicand shifted left 3 times. If it is 32 bits, here I have shifted left 4 times plus shifted left 5 times. The next addition is shifted left 6 times plus 7, so and so on. So I will put parallel adders. For the 32 bits, there will be 16 adders, which they are adding together, and the result coming out from them. Then I will use these partial results and add them together. Again, it coming here, I will use these results and add them together 2 by 2, and then at the last step, the whole thing will be added. Isn't it correct? So I am adding in parallel in how many steps? 16 add here, 8 add here, 4 add here, 2 add, and 1 add. 1, 2, 3, 5 steps. Instead of 32 cycles, we are just using 5 cycles to calculate the multiplier. So it is very fast compared to 32 cycle times that we use. In the first algorithm, we just had 32 add, and it takes 32 cycles to produce the result. Here, we just have 5 cycles, but so many adders we have used. We have used 16 plus 8, 24, 28, 30, 31 adders that we have used here instead of 1 adder that we had before. So if the speed is too important for you and you could provide more resources, more adders, then you could use this architecture. If not, you may do it by 1 adder and do it in serial with 32 steps. We might be able to do it as a pipeline, so we don't need 31 adders. Instead, we just need 32 adders. So the first stage, 32 add, then the results are coming back to the next stage of the pipeline for the next addition, for the next addition, and for the next addition. So we can just use pipelining to reuse the adders that we have used in the first stage. In MIPS, there is an instruction for multiplication. And so the hardware that we have shown you, it will be used in the MIPS to calculate the multiplication. So 2 30-put registers will be used for the MIPS to be multiplied, but we told you when there are 2 32 bits multiplicated, then the result could be 64 bits. But we don't have 64-bit registers in MIPS. What does MIPS do for that? So it will bring 2 new registers called high and low. There are 2 new registers. So the result will be stored in high and low. So let me say, for example, this is, let me write, multiply register S0 with register S1. So this is the instruction. When we have this instruction, S0 is 32 bits, S1 is 32 bits. They are multiplicated. Then the product would be 64 bits. 64 bits. So it is 2 32 bits. The high word, yes?
Does this relate to like using load upper immediate or immediate at all?
If you want to load something for S0 or S1, yes, but it might have been calculated before. Whatever S0 is S1 are there. So there are S0. So for example, you want to multiply 8 by 12. So you put, for example, or I S0 virgule comma 0 comma 8. So now S0 is 8.
I'll just do the lower part of the instruction, right? Or the
Yes. The immediate is 16 bits. So if it is more than 16 bits, then you have to use load upper immediate. You do it in 2 instructions: load upper immediate and then OR with the lower part. So whatever S0 is there. So S0 is a 32-bit register. So either you have loaded or either you have calculated it, either you have loaded from the memory, you got 32 bits from memory, so it is there. Then you write mult S0, S1. The result will be 64 bits. At the 64 bits, we don't have a register 64 bits. So MIPS brings these 64 bits, it separates them, it breaks them to 2 32-bit registers. One is called high, the other is called low. So the result, the product, will be stored in 2 registers. So how do we use them? Now the results are in high and low registers. How do we access them? So this is the instruction multiplication, and then the result would be in high and low registers. To get the high and low register, we have a specific command instruction. Move from high and move from low. So if you write, for example, move from high S2. So it brings the high value to S2. And you know, high value is the most significant 32 bits of the product. And you could do the same for move from low and bring it to the destination that we want. So that is the instruction that we can use in multiplication. So you could test high value if it is more than 0. If it is not 0, then it means that the product is more than 32 bits. If you are doing some kind of only 32-bit operations, then it means that there is overflow. But you could also use the high value to use it for more instruction. There is a pseudo instruction in assembly which accepts 3 operands, and it will multiply RS and RT together, and then the result, the low part of the result, is stored in RT. So this is, again, as I repeat, it is pseudo instruction. To do that, assembler make several instructions. First, mult, and then load from low and put it in RD. So it is 2 instructions coming from multiply RS and RT, and then move from low to RD. So this is a pseudo instruction. It's good if you know that your product is not more than 32 bits. Least significant 32 bits of product will be put in RD, the low part. Okay, so that was the multiplication. Now we are going to division. So multiplication was more complex than addition. Now division is more complex than multiplication. So let's do division. Again, exactly what we have done in the school, the high school, or even the elementary school. Division is taught in class 3, yeah? 3 or 4, yeah, it's not 3 or 4. Okay, so let's do the division. I start with a decimal division. So I am adding, I am dividing, let's say, 835 to 63. I hope I do it right. It's hard when I'm doing in front of you. So the first thing, 63, so we can start by separating 2 digits from the dividends. 83 to 63, we can have 1 here. So we put 1 here. 1 times 63 becomes 63. Then we subtract 63, it is 200. Then we bring 5 down. So it becomes 205. 205 divided by 63. 3 is good. So it is 3. 3 times 63 is 3 times 3 is 9. 3 times 6 is 18. So 9 out of 5 is 9 out of 15 is 6. Then we have 7 out of 10 is 3, and that's 36. And that's it. So we have the remainder of 36, which is smaller than the divisor, and the quotient is 13. So 835 divided by 63 will result in 13 with a remainder of 36. Okay? Did I do it right? No? There was mistake?
Remainder is 16.
What's 16?
Remainder?
Oh, the remainder 16? Yeah, you are right. 8 out of it is, so what we have a borrow, so it becomes 9. 9 out of 10 is 1, and then yes, okay, 16. And you know, when you do the divide, you have 4 numbers: quotient, remainder, and at the first you had the dividend and the divisor. So the equation would be dividend is quotient times the divisor time quotient plus remainder. So, and the remainder should be less than the divisor. Okay, you know this from the school. Now we can do the same for binary. We are dividing a number of 1001010, so it is a 7-bit number, divide by 1000. Again, we start with subtracting the divisor time 1 from the dividend. So we put 1 here. 1 times 1000, it becomes 1000. Then we subtract them together. Maybe it's good if I write it here so you know the steps. So the first one would be 1. 1 times 1000 becomes 1000. Then we subtract. So 0, 0, 0, 1, this is the subtract. And then we bring 1 here, 0. So it doesn't fit that. So we add 0 there. So 0. Then we bring another. So it is 1. So it still doesn't, it is still divisor is less than the new dividend. So again, we put another 0 here. Then we bring this one. So it is 1010 and it is 1000. So now we have 1 times that would become 1000. Now we subtract 0, 1, 0, 0. So the remainder is 10, it is 2, and the quotient would be 1001. If you do it in decimal, you know what we have done. So this is 2 plus 8, 10, plus 16, 16, 32, 64. 64 plus 10, it is 74, if I am not mistaken. And the divisor is 8. So 64 divided by 8. 64 divided by 8. 74 divided by 8. Okay, yeah, we have some. So online people, if there is no audio, please let me know. 74 divided by 8, the result was 9, the remainder is 2. 9 times 8 is 72, plus 2 is 74. So I did it correctly in binary. Sometimes it is hard to do that. Again, you'd see if the dividend is the sum of the bits of the divisor and the quotient, that's because it is the reverse of the multiplication. Here, our dividend is 7 bits, the divisor is 4 bits, and the result of the quotient is 4 bit also. Okay? So what did we do in our algorithm? The steps were this. So we check for 0 in the divisor. If it is not 0, because you cannot divide by 0, then if divider is less than divisor, if divisor is less than that, that's good. So we subtract them. And then we have 1 in quotient. If it is not, then we have 0 in quotient, and then we bring down the next dividend bit. Exactly what we have done for dividing. So how do we do it in hardware? Exactly as we talked. So again, in the hardware, the algorithm would be something like that. We start from the initial values. We subtract the, why it's got, yeah, it disconnects people, online people. Sometimes I feel that it is disconnected. No? You hear me continuously? Yeah? Okay.
Yes, I do, yes.
Yes, I do,
Yeah, yes.
okay. So why sometimes we feel that it's got connected. Okay. What do we do here in hardware? Because in the things that I have done here, I will look at the divisor, and if it is less than the dividend, then I bring it down and do the subtraction and put 1 in the quotient. But by seeing that, because I am human, I can see that. But in hardware, we have to make a comparator or something. Instead of that, we subtract in hardware. We subtract divisor from the dividend. If the result is negative, means that it was not less than dividend. So we shouldn't have done that. We put it back again, we add it back again, and put 0 in the quotient. So here, look at here, subtract, it says subtract the divisor register from the remainder register and place the result in the remainder register. So the remainder register is updated, which might not be correct if the result is negative. Test remainder. If the result is negative, it means that we shouldn't have done the subtraction. Again, we restore the original value by adding the divisor to the remainder. So it goes back again to whatever it was. If it is positive, then it's good. It means that we should have subtracted divisor from the remainder. So it's good. So we put 1 for the quotients at the right, and then we go to the next stage. Here, if it is not good, we restore the original value of remainder and then put 0 for the quotient. So go to the next page. I will show you, I guess, in the next slide, how do we do that. So this is the restoring division, because we restore, we update the dividends. If it is wrong, then we restore it. So we call it restoring division. And this would be the hardware. As you could see, the hardware would be something like that. So starting with divisor, we shift divisor by right 1 time, and then subtracting from the remainder. If the result is negative, then it means that it is bad. We have to restore it again. If not, it's okay. So let me show you here. Now we are going to divide 7 by 2. 7 is 0, 1, 1, 1. 2 is 0, 0, 1, 0. So let's start step by step. In each step, we subtract, and if it is negative, we restore. So let's start. The initial value of quotient is 0. The divisor is shifted left by 4, because we are doing 4-bit registers, and the dividend could be 8 bits. So we make the divisor 8 bits, and the remainder is first initialized with the one we have, 7. So the remainder is 7. The divisor is 2 shifted 4 times. So this is the divisor. So what do? We start by subtracting. So we subtract divisor by remainder. It is negative. You see it by eye, but in the hardware, we have to subtract it or have some kind of comparator circuit. But we just subtract. We subtract remainder with divisor. So it is negative. You see, remainder is this. The divisor now is 1, 0, 1, 0 something. It is bigger. So the result became negative. This one is the sign bit. It shows that the result is negative. Since the result is negative, we have to add it back again to the remainder and restore the first remainder that we had, and we have to put a 0 in the quotient. Okay? Next stage. We shift right divisor 1 bit. Now the divisor is 0, 0, 1, 0, 0, 0, 0. Still, this is less than the dividend. So if you subtract them, you get the negative result. Since the result is negative, you have to add it back again and get the remainder as 1, 1, 1. And again, you have to put a 0 in the quotient. Now we again shift right another one. Shift right, so the divisor is now 1, 0, 0, 0. And the dividend is 1, 1, 1. Still, this is bigger than that, greater than that. So if you subtract them, you get the negative result. Since you got the negative results, again, you put a 0 for the quotient, and then we are going to shift right the divisor again. So shifting right. Now, when you shift right it, you have 1, 0, 0. And then if you subtract it from 1, 1, 1, the result now is positive. You see, the result is positive, and the subtraction is 1, 1 now. Okay, 1, 1, the result is positive, so we keep that, we don't restore the original value, we keep this, and we put a 1 in the quotient now. So the quotient gets a 1, and the remainder is changed. Now again, we do a shift right for the divisor, so shifting right the divisor. So it becomes 1, 0. So it is 1, 0, and the dividend is 1, 1, we subtract them, it becomes this, and it is positive, because this is greater than this. So it is positive, now this is positive. So we keep it, we put another 1 in the quotient, and then we go for the next stage, which will be the last stage. We shift right the divisor. The divisor is now 1, and the remainder is 1. So it is the last stage. We have done 4 shifting, because we had a 4-bit number. Shift stage is enough. So that's it. Now you have the quotient, which is 3. You see, 3. And you have the remainder, which is 1. Which is correct. We divided 7 by 2. The quotient becomes 3, the remainder becomes 1. But you saw that it needs 4 stages, and in each stage we are doing 3 things, 3 steps. Subtracting, checking if it is negative, and based on that either putting 1 or 0 to the quotient. So the hardware for that would be something like that. And then again, we are shifting them. We are doing we are shifting divisor and dividend. Instead of that, we can put a 1 shifter and do it again. It's the same thing that we have done for multiplication. So the hardware seems very similar to the multiplier. So you can put some kind of a configuration to make it universal. Again, I am telling you some good questions for the exam. So for your exam, you could design a universal multiplier divider with the same hardware. In multiplication, we were thinking that we can put more adders, so we add them in parallel, 2 by 2. Could we do that? Could we do the same in division? Anybody? Any guess? Online people. Remember, in multiplication, I told you that if we put more adder, then we could make it faster. We can do it in parallel. More adders.
I know there's something called like division by invariant multiplication,
okay,
which is used in some places.
So the things that McQueen is suggesting, that we use multiplication to find the division. We do multiplication and see if the result is good, then we keep it. If not, we can change the multiplicand and do it again. But no, before that, I am asking you the same concept that we have used in multiplication. Remember, in multiplication, I told you that you can use 16 adders together at the same time, and you add 2 by 2 of the multiplicands shifted left different bits. This will add multiplicand shifted nothing with 1 shift. This will add 2 left, 2 shift with 3. This will add 4 with 5, and so on. And then the sum of these things will be added again. This is how we have made a fast multiplier using multiple adders. Could we do the same thing here? In division, we have subtraction instead of addition. Could we use that? Think of the division. We subtract, then we look at the result. If it is negative, we restore it. If it is positive, we go to the next stage. So based on what I've told you now, is it possible to do all of the subtraction in parallel? No. Why not? Because the procedure is based on the result of the subtraction. If the result is negative, we should disregard that subtraction and do it again, return it, restore it to the original value. So because of that, we cannot do the same concept for division. So we cannot use it. We cannot use parallel hardware as we used in multiplier because it is based on the sign of the remainder, and there are different hardware for that, which we are not going to that now. So let's, what about sign division? Up to now, we were looking at the number as unsigned numbers. So what do we do for sign division? What's your suggestion? In a school, how do you sign division? If I ask you what is the result of minus 15 divided by, let's say, divided by 4, what's the result? How do you do that? Huh? You divide by absolute values, and then you think of the sign. Yeah? Is that correct? So what we do with minus 15 divided by 4. So we do it 15 divided by 4. 15 divided by 4 would be 3 quotient, and the remainder 3. Yes? So what about minus 15 divided by 4? So the quotient would be minus 3, and the remainder would be minus 3 also. Okay? Yeah? Isn't this the way that you're doing the sign division? I guess you haven't done that before. And it needs some kind of definition. Let me do it for you. We make them absolute value, positive value, then we divide, then we think of the signs of quotient and remainder. So let's do it. This equation should always be correct. For example, in my example, minus 15 divided by 4. So still, we have to get 4 times divisor times quotient. Quotient, I told you it is minus 3, plus the remainder, which was minus 3. Is it correct? 4 times minus 3 is minus 12, plus minus 3 is minus 15. So it is correct. So this is the quotient, this is the remainder. Somebody might say that why I don't make this minus 4 and make this plus 1. It's still the same. Let me write it for you. Minus 15 equals 4 times minus 4 plus 1. In this way, 1 would be remainder, minus 4 would be quotient. Which one is better? we need a definition here. So the typical definition, which is good for also operation, because we wanted to use the absolute values, is this one. We use this, not this. Because the definition of remainder, when you are talking about signed numbers, negative and positive, is different. It should be different than the unsigned number. So we don't use this. Here you see, dividing, let me show you all the combinations of division. So I divide 7 plus 7 by plus 2, then minus 7 by plus 2, then plus 7 by minus 2, then minus 7 by minus 2. Let's do it. The false positive is simple. We know that. 7 divided by 2 becomes 3, and the remainder is 1. So still, if you multiply 3 times 2 and then add the remainder, you get the dividend. Okay? So what about this? Minus 7 divided by 2. So one solution would be, as I told you, you make the absolute, so 7 divided by 2, the quotient would be 3, and the remainder would be 1. But since we have minus 7, the quotient it becomes minus 3, the remainder it becomes minus 1. And here we don't go for quotient as minus 4 and the remainder is plus 1, because you want to be similar to this, which is the absolute value division. So we use this notation, not that one. Now see 7 plus 7 divided by minus 2. Again, we use the absolute value would be 3 and 1. And what about the signs? The quotient. The quotient sign is simple. The quotient sign is always the signs of the dividend and divisor. If both of them are negative, the quotient is positive. If one of them is negative, one of them is positive, the quotient is negative. If both of them are positive, the quotient is positive. So the quotient sign is simple. Now we have one positive, one negative, so the quotient is negative. But what about the remainder? The remainder gets its sign from the dividend. If the dividend is positive, the remainder is positive. If the dividend is negative, the remainder is negative. So remember that. Minus 7 divided by minus 2. Let's use this rule. Minus 7 divided by minus 2. We do the absolute. 7 by 2. The result would be 3 and 1. 3 as quotient, 1 as the remainder. So what about the sign of quotient? Since both of them are negative, the quotient will be positive. So the quotient will be plus 3. What about the remainder? The remainder gets its sign from the dividend. The dividend is negative here, so the remainder is minus 1. You know, you learned? Follow. So negate the quotient if the signs of the operands are opposite. If they are opposite, then the quotient is negative, and the remainder will be the sign of the dividend. Okay, we are done. So let's do the attendance. So go to the attendance, the password for that. Online people and in-person present people here, both of you do it. So the password for the attendance is 223-07-14. Rudra, I guess the time for the quiz has changed. I haven't seen that. You should have talked with me. at that time. So 2023 07 14. Was that right? Did it work? Work?
Yeah.
No? Let me see if it didn't work. Maybe I am. So where is that? Quizzes. You see the quiz, yeah, but the password is not correct. Yeah? Nobody?
I don't see anything.
Did you see the quiz?
Yeah, I did the quiz.
It worked. Okay. So the quiz is here in the computer arithmetic section module. So let's see if it is there.
Oh, there it is.
Attendance, July. Where is that? Oh, it is not here. I have to add it here. So
Under the quizzes tab.
yeah, you could go to quizzes and see it, but I will bring it for you also there. So, so if you go to quizzes, you will see there. Otherwise, I will add it for you right now. Add activity, quiz. It is very complicated, actually. Where is the quiz? Attendance. Where is the quiz? I don't see it. Attendance. This is not the one. This is not the one. This is the one. Oh, okay. No. No, July 2nd, no. I can't find it. I hope you did. The password is 2023 07 14. So you found it, yeah? It is in quizzes section. I don't know why it's. Oh, here. It's here. No, it's July 10. Where is July 14? I don't see it. Too complicated. I hope you found it. Everybody okay with the attendance? Yeah? Done it? I couldn't find it, so you did it better in quiz section.